Okay, so let's go back and say what we're talking about. This one is going to be the federal minimum income tax, and like I said, it's forecasting. The reason we're doing it is to forecast the population mean, all right? We know the population standard deviation. We have taken a sample and we've calculated the sample mean, but we're really interested in the population mean, and that's going to be true of every single problem that you are doing for these chapters, all right? So let's see if we can come up. This is not the best way to do this, but let's try it anyway. See if we can come up with our calculations, all right? I put down important parts of the problem. It told me I had a sample size of 45. It said that I did a sample mean of 4242, and I came up with I had a population standard deviation given to me of 991, and I want a 95% confidence interval. You can start at any place you want to, but when I see 95% confidence interval, I think alpha. Well, alpha for this one, or a confidence interval for this one, is going to equal, I guess we could call it like that, it's going to equal 0.05, right? Confidence interval 0.95, 1 minus 0.95 is going to give me my alpha. I didn't mean to scratch through that, sorry. And for confidence intervals, I always divide alpha by 2. So I've got 0.025. And, you know, I'm going to be looking this up as a z-table. Why z-table? Because, you know, I have the population standard deviation. So since I have that, it's going to be on the z-table, and I'm going to look up and I'm going to find that my z-score is going to be 1.96. Now, it's easy to find that one, and we've done it so many times for that particular z-score that I almost just don't even look it up anymore. But let me show you that on this particular test, you will not need the positive side of the z-table. Hint, hint, okay? You're only going to need the negative side. Every question that is asked is going to use an area that's in the tail, okay? If you're looking up an area in the tail, that's always going to be on the negative side. If I was looking up something on the right side, it's not in the tail, it's the opposite of that. You see what I'm saying? So even if the question is about z to the right of something, you're going to look it up over here and just know that it's on the other side, right? I mean, we're going to use this side of the table exclusively. So I'm going to go down to where I see 0.0250, and of course that is a negative 1.96, isn't it? And for z-scores, for confidence intervals, I'm going to use it in a calculation. I just use 1.96 is all I use. And then I know my confidence interval has to be like this. Confidence interval is always equal to that sample mean plus or minus, plus and minus the margin of error. And that margin of error is equal to the z-score times the standard deviation of x bar. You can look that formula up. Don't mess it up, okay? You're going to have to adjust every standard deviation that you got. So for this one, I have to take this standard deviation. I can't seem to write today. I want to get the standard deviation of x bar. So I take the standard deviation 991, I divide it by the square root of the sample size, which is 45. And when I did those calculations, I came up with 147.7296. Go to 4 decimal places with all of your standard deviations, okay? All right, I know I'm going through it quick. It's the only way to get through all this material. And then you may have to go back later and make sure you know how to do these calculations with your calculator, okay? All right, so I need the margin of error. That margin of error is going to be equal to the z-score of 1.96 times the adjusted standard deviation of 147.7296. And I come up with a margin of error of 289 point, and I'm going to round it at this point to 2 decimal places because that's where it told me to round to, okay? But don't round the margin of error to 2 decimal places. Don't round your margin of error smaller than 4. Use it because you got to use it in more calculations, okay? So then all I've got to do here for the confidence interval is say, well, it's equal to that sample mean, 4242, plus and minus that margin of error, which is 289.55. And I have a high number, and I have a low number and a high number. When I subtract 289.55, I come up with 39.52.45. And when I add it, I come up with 45.31.55. And that is my confidence interval. And the other thing you need to know about the confidence interval is, what is it telling you? Well, I'm 95% confident, okay? Why? Look, it's a 95% confidence interval. I'm 95% confident that the population mean is between these two numbers. And those words I just used are important. What are we trying to forecast? The population mean. No reason to forecast the sample mean. We just took it and calculated it, right? So the whole deal with this is we're trying to tell more about the population data. Okay? Everybody good with that one? Let's do one that has the sample standard deviation that's given to us instead. Let's see if I can find that one. Number 39 is where I went with it. Got tons of lists up here. Can't seem to get all my act together. Okay, so we have each employee of a large company encouraged to contribute through payroll to an international charity, and contributions follow a normal distribution. Okay, well, that's kind of important to us. This is where we start really finding our data. You take a random sample of 25 and you find that the sample mean annual contribution is 501. So we've got a sample of 25, sample mean of 501. And then look what it says, with a standard deviation. Now, it doesn't say anything about the population. It says, we took this sample, we found the sample annual contribution and the sample standard deviation, right? That's how you know that this does not have a population standard deviation given to you. It was talking about the sample here, it's still talking about the sample here. So we have a sample standard deviation, and we want a 99% confidence interval for the population mean, rounded to 2 decimal places at the end. So what did it tell us in this problem? Well, number one thing it told us is that we had a sample of 25. And from that sample of 25, we got a sample standard deviation of 501. And then it kind of says, okay, so there's from that sample, I also calculated a standard deviation of, I said sample standard deviation, I'm going to say sample mean. I calculated a standard deviation of 17, and I want a 99% confidence interval. Where does that population mean lie? Now, when I'm dealing with a confidence interval that does not give me the population standard deviation, and that's key, guys, okay? It didn't give you the population standard deviation, so all you have is the sample standard deviation, okay? So it's, I've got to use the t-table. So I know when I come up here, I'm going to say t is equal to something, but let's figure out what parameters we're going to use for t. When we use the t-table, we've got to have degrees of freedom. Well, we know that if the sample size is 25, the degrees of freedom is 25 minus 1, right? So I got a 24 is my degrees of freedom. And then I need to know what alpha is again. Well, alpha is 0.01. This is 0.99. Alpha is 1 minus 0.99. So I got 0.01. I always have to divide alpha by 2. 0.005 is what I get alpha divided by 2. And that tells me in the t-table where these two numbers right here are going to tell me my t-score, okay? So I'm going to go to the t-table real quick. And I'm going to say, and the t-table, you use both sides of this thing, okay? There's no positive or negative side of the t-table. We just, degrees of freedom is the thing that you're, going on. Degrees of freedom is 24, so it's over here. That's the first thing I look up is find degrees of freedom 24. And then I want to say 1/tail of it is 0.005. Why 1/tail? Because I divided it by 2, didn't I? So 1/tail of it is 0.005. And I've got to find the column that says alpha level for a 1-tailed test, 0.005, that's it. Look, if it had been a 2-tailed test, it would have been before I divided it by 2, okay? So I've got this one. I really think that you're smarter just to always use this row for your delineations, okay, because otherwise I think you'll get confused with what it's telling you. But this point, 0.005, look, it's a 99% confidence interval, so you kind of check yourself, right? So I've got 0.005, and I go down to degrees of freedom, 24, and I get 2.7969, and that's what I'm going to use for my t-score. 2.7969. Now, the note pages that you've got I only went 2.797 is what they rounded to. I'm going to give you the numbers. I'll try and redo these calculations for you because the old t-table that we used with the other publisher only went to 3 decimal places, but these t-scores are always going to go to 4. And I have just finished going through your final exam and fixing it so that all the t-scores on that thing go to 4 decimal places. So I think you'll be consistent on the final, okay? So now what do? Well, the standard deviation of x bar has to be calculated same way. I take it and I divide it by the square root of the sample size. So this is really 17 divided by 5, isn't it? And when I do that, what did I get? 3.4. Well, that was easy. I didn't have to go to 4 decimal places. And next, I'm going to say my confidence interval for this thing is equal to, well, this time it's the formula is this. It's equal to the sample mean plus or minus the t-score times the standard deviation of x bar, right? Which is, this is the margin of error, plus or minus margin of error. Okay, plus and minus. I have to watch everything I'm writing today. All right, so what is the margin of error? Well, it's going to be 2.7969 times that standard deviation of 3.4, and I'm going to round that to 2 decimal places because that's where I can, and I need to recalculate this because last time I only used 3 decimal places. Let me see what it comes out to be. 2.7969 times 3.4, and I get 9.51 is what I'm getting. What did I get last time? Yeah, that's what I got last time anyway. The 4th decimal place didn't really change anything too much, okay? I'm going to round it there because I'm going to be adding and subtracting over here. What am I going to add and subtract? Well, I start off with the sample mean. It came up to 501. I'm going to add and subtract 9.51. So when I do that, I have the lowest number it could be is 501 minus that 9.51, right? And that would come out to be 491.49, and 501 plus that would be 510.51, and that is where I am 99% confident my population mean lies, is between those 2 numbers. Are we okay so far? I know I did a lot of this last week too, so we're going through some of the same stuff again, but I think that's the best plan. These are the most complicated problems we have to work in this class. You know, you've hit it. You've gotten to the final exam. Yay, okay? And this is the most complicated it gets. You do have a good selection of problems on here that's representative of what we're working, all right? You good for that one? All right, let's go to the next one. So I want to do another confidence interval, and this time I'm going to take you to a proportion problem confidence interval, okay? Number 40 I picked for that one. Let's see if I can find it. So number 40. Here it is. So number 40 says that there was a 1997 poll of 261 male married upper-level managers. Now that's probably going to be my sample size, 261. And it says that in that poll, 31% of the men stated their wives worked either full-time or part-time. And at that point, I know this is a proportion problem because it's talking to me in percentages, right? 31%. Not, you know, I mean, it's just, it's needing, the data is in percentages, okay? And then it also tells me down here what's the boundaries for the 99% confidence interval for the proportion, which is P, is called the population proportion. And it wants to know the proportion of all male married upper-level managers whose wives work, is what it's asking about. All right, now it doesn't give me a standard deviation. Another hint that it is a proportion problem. If they didn't say that, confidence interval for the proportion, you'd know it because they didn't give you a standard deviation to work with. Because proportion problems, you calculate the standard deviations using P times Q or P hat times Q hat divided by the sample size, and we take the square root of all that, right? Got me? Yeah, okay, yeah, you're nodding. Good. So let's go see what we can find that we know with this particular problem. And with this particular problem, I know that they want a 99% confidence interval. I know that the sample size was 261. And I also know that they ended up with a sample proportion of 0.31, 31% for this one. Now, the sample standard deviation of the sample proportion has to be calculated. Look, you've only got p hat to work with, okay? So you have no choice. You're going to have to use p hat and q hat. This one doesn't really cause us any moral issues here. We don't have to decide between, am I using p times q or am I using p hat times q hat? You were only given one of them. So you got to figure out, if p hat is 0.31, somebody tell me, what's q hat? 0.69. Is that right? Got to tell you, I've still got a cold, so I'm struggling with everything. Okay, so we got 1 minus p hat is q hat, right? P hat plus q hat equals 1. And then we can calculate the standard deviation of p hat by saying that's the square root of 0.31 times 0.69, and we divide it by the 261, that is the sample size. Now make sure that your calculator is doing what you think it is doing when you calculate these. I know I'm doing a lot of the math for you up here, and that's is because of time, because you are a hybrid class and we simply don't have time for you to work all these problems. But what you have to do is go back through and make sure that when you do it with your calculator, you end up with these same numbers, all right? Otherwise, you're going to say, oh, wait a minute, maybe I was supposed to put parentheses in there somewhere and I didn't. So when I came up with this one, and I need to go to 4 decimal places with my standard deviation on this one, I came up with 0.0286. Okay? So I go 4 decimal places. Now, listen, and I've checked. I've worked every problem on your final, all versions of it, and I've worked some of them twice. And you're good on all of the standard deviations, even proportion, if you go to 4 decimal places, okay? Because proportion problems have a lot of decimal places. Sometimes it has, in the past, you have not been close enough with 4, you'd need to go to 6. But you guys are okay with this one, okay? So 4 decimal places on every standard deviation, you should be okay. So what else do I have to do here? Well, let's see, I need to say confidence interval, right? And because this is a proportion, I know, because it's a proportion problem, I know I'm going to use the z-table. I need a z-score. I got to come up with alpha. Well, if this is a 0.99 confidence interval, alpha is 0.01, and confidence intervals always divide alpha by 2, so I got 0.005, and that's what I have to look up, okay? So I go to like I told you, you don't need but one side of that z-table. I go to the negative side, I look up 0.005. In fact, that's the only place you're going to find it anyway. 0.005, where is it? Here it is. It's between these two. 2.57, 2.58. Generally, we go with the larger number here, and I think I did in all of your examples, but you should be close enough if you choose either one, or if you choose to split the difference and go 2.575, okay? It should still be close enough. I can't remember what I did in your notes. Let me look and see. I did 2.58. So let's go. Z is equal to 2.58, and that's what we're going to use. Now, what's my confidence interval? Well, it's kind of the same thing. It takes the, this time instead of sample mean, it takes the sample proportion, and it says add or subtract the margin of error. Well, the margin of error is equal to Z times the standard deviation of p hat. Okay, margin of error for this one, 2.58 times the standard deviation 0.20286, is going to give me, what did I get for that one? 0.0738. And this one went to 4 decimal places. I assume it told us to. And I take my confidence interval p hat, which was 0.31, and I say add and subtract 0.0738. When I subtract it, the small number I get is 0.2362, and the large number I get is 0.3838. Now, other thing about proportion problems, sometimes they'll ask you for the answer in percentages. It's simple. If they ask for the answer in percentages, or like you have a multiple choice test, right? So if it gives you answers in percentages, well, you just move the decimal 2 places. This is saying between 23.62% and 38.38% of all the population is going to fall between those two. So it's going to fall between those 2 percentages, right? I'm sorry, it's because 99%. We're 99% certain it's going to fall between those 2 percentages. Should I say that again? Did I mess it up enough that you understand what I'm saying? You guys okay? So it's between those 2 numbers or those 2 percentages. That's my confidence interval. And that is your 3 types of confidence interval problems that you're going to be required to understand. What if they give you a population standard deviation? What if they don't give you a population standard deviation? And what if it is a proportion problem? So that you can look back on the list that I gave you and you can make sure you can work each of those types of problems, okay? And let's talk about the 2 sample size problems. One is going to be sample size for a population. It gives us a population standard deviation. And the other one is it's a proportion problem, okay? So we've got 2 different cases we can run into with these. We don't have the sample standard deviation thing because we really won't have the sample yet. And the only thing it might happen is they might say a preliminary sample was taken and the preliminary sample gave us a standard deviation. Now listen, if they did a preliminary sample and that's the only standard deviation you've got, well then you go with using it like you pretend it's the population standard deviation, because that's all you can do, okay? All right, let's take a look at, what did I get? Which problem? Number 42. Let's see what it says. Okay, so problem 42 says, determine the sample size that is required for estimating the population mean. The population standard deviation and the desired margin of error are, well, population of 150, they want a 94% certainty here, and the margin of error is 3. Now, that one is worded poorly. I'm just going to tell you, it will be worded a lot clearer on your test, but what you should have picked out of there is, I need a sample size. I need n, right? I need n is equal to whatever. And I would go, if I wasn't certain what I was looking for, I would go and look for my sample size formulas, which are in chapter 8, right? And here it is. N is equal to z squared times standard of deviation squared divided by the margin of error squared. So if I don't know n, I need these 3 pieces. And it gave me these 3 pieces. So I'm going to go over here and say, well, n is equal to, what did it start with? Z squared times the standard deviation squared divided by the margin of error squared. So what is that equal to? Well, I got to figure out, did it say 94% really? Or did I mess that up? So that's an unusual one. I guess it did. Yep, it did. So I got to come up with this confidence level, right? So what I'm going to do is say, well, alpha is equal to 0.06, isn't it? And also need to divide alpha by 2, and I'm going to get 0.03. And because I'm dealing with a z-score, I'm going to look up 0.03, which is not one of my normals. On the negative side of the table, 0.03. Where did I get close to with this one? Well, about as close as I'm getting is 1.88. I think that's what I used for that one. Yep, you see it? Okay, so I got 1.88 is what I'll use for z. And now I know everything, so all I have to do is plug them in. 1.88 squared times the standard deviation of 150 squared divided by the margin of error, which is what I hope it will be. You know, I'm only willing to go for a 3 margin of error. And when I did all of that and plugged it in, you should be able to do all of that in one step in your calculator. Comes up to be 8836. No, I'm not sure if it came up with any decimals or not, so I've got to do this again. Hang on just a second. So I'm going to say 1.88 squared times 150 squared, and then I'm going to say divided by 3 squared. It should do, okay, it was exactly 8836. Guys, if it came up with a decimal, you would simply bump up to the next number because you need whole numbers for sample sizes. We don't have decimals. If it came out to be 8836.2, you go with 8837. You always bump it up. I hesitate to say round, and they say round up, but what I'm telling you is you always go up to the next one, okay? It's not a rounding issue. It's the fact that you can't have a fraction of a person. You can't survey a fraction of a person. You have to survey a whole person. Does that make sense? Yes.
When I was doing the homework for chapter 9 or 8 in Canada, it was saying that you had to divide the margin of error by 2, and then you had to square it back instead. Is that something different, or is this the correct way?
This is the correct way. The margin of error is not divided. But if you'll send me that, this is a new set of software, I'd like to see it so I can, report it, because that's, your margin of error that's given to you. I can't think of any reason to divide that by 2. I can think of a reason to divide alpha by 2, but not the margin of error. Okay? All right, so that's that one. Let's see. Let's go to the next particular one is another sample size, but it's dealing with a proportion, and it's number 37. I'm getting there. Okay, so this one says the Labor Bureau wants to estimate at a 90% confidence level the proportion of all households that receive welfare. There was a preliminary sample that showed that 18.5% receive welfare, and the sample size that would limit the margin of error to within 0.036 of the population is what we got here. They want to limit us to within 0.036. Did you say they said multiply it by 2 or divide it by 2? You said they said divide. Yeah, that doesn't make sense. Okay, never mind. I just had another thought kind of run through my head, okay? So anyway, let's see what this one looks like as a proportion problem. And we're going to go to number 37 here. See if I can find my notes on it. All right, so what I want to come up with first is if I've got a 90% confidence level, then, and for proportion problem, I mean, for these sample size problems, I'm never using T. I'm always using the Z table for sample size. What I've got to say is alpha is 1 minus 0.9, which would be 0.1, and alpha divided by 2 would be 0.05. And so then the Z score for this one is going to be, okay, we would look it up, right? 0.05. And I'm coming between these two numbers. It's going to be 1.64, 1.65, and generally we just go up, because if I hit between them, I would go 1.645, and that would round up to 1.65. Is that what I did in the notes? Let's make sure I was consistent here. Yeah, I did. Okay, so I've got that, and then I need to calculate the standard deviation that I'm going to get to use. Well, they gave me p hat. And p hat here is equal to 0.185, isn't it? Change it to a decimal, right? So if I've got 0.185 for p hat, then q hat is going to equal 1 minus 0.185. That one I would definitely use a calculator to do, guys, okay? I mean, most of these p hat and q hat things you can do in your head, but this one came out to be 0.815. Now, I can calculate the standard deviation of p hat which in this proportion, oh, I'm sorry, I don't need to calculate it. I'm going to use p hat times q hat, or p times q, but I don't have p times q, so I've got to use p hat times q hat to do this, okay? So I'm going to say the sample size here is going to equal z times p times q squared over the margin of error squared, right? And since I don't have p, I'm going to be using p hat with those. So and the only thing is to keep in mind is you have to square the z still, you have to square the margin of error still, but p hat times q hat leaves you with that option of you don't square them, you multiply them together because they're kind of different. They might be different. The only time this will change on you is they say the most conservative sample size. Do you remember that problem? If anybody asks you for the most conservative sample size, you use p hat and q hat have to be 0.5. Both of them are equal to each other. That's your most conservative sample size, okay? So just keep that in mind. So I've got 1.65 squared times 0.185 times 0.815, and I'm going to divide this by whatever they told me I could have, 0.036, and I square it. And what I came out with is 316.7. And of course, I would say that's a sample size of 317. How are you doing so far? Good? I know we've gone over this before, so it should just be a refresher for you. Because next we're going to do hypothesis test. And I tried to pick one of each type for you. This is what I tried to do. Okay, so you've got 3 different hypothesis tests. I know this population standard deviation. I don't know the population standard deviation, so I have to use the sample standard deviation, or it's a proportion problem. You also have this issue going for you. It could be a one-tailed test, or it could be a two-tailed test. If it is a one-tailed test, it could be in the left or the right tail. If it's a two-tailed test, it's always going to be split. What difference does it make? Well, in this one, we split alpha in 2. In these 2, we don't divide alpha. And that also matters for when you get your p-value. When you calculate your p-value, you're looking up the area in one tail, right? When I look up the area in one tail of the test, and it's a split test, I have to multiply that area times 2. So that will mess up your p-value if you forget to multiply times 2 in the case of a two-tailed test. Are you following me? Okay? All right, so that's the issue with whether it's one-tailed, two-tailed, whether it's left or right. Now, whether it's a left or right, we're still dealing with the areas in the tails, right? So we're still going to follow what I told you. You're still going to be looking up these areas on the left side of the z-table. You still don't need the positive side, but you do have to know that if you have a right-tailed test, you have to know that that z cutoff score, that critical value for z, is positive, not negative. Are you following? You should have hit this in your homework. But if you haven't, you know, why is it, I looked up the value for z and it came out to be negative 1.96, and why is it saying it has to be positive? Well, it's possibly that it's a right-tailed test. If it's a right-tailed test, the z critical value for z is always going to be positive. It's always on the right side. And that's one reason that it's useful for you to draw the curve, okay? All right, so let's see what we can do with these 3 examples I've got. First one is problem number 66. So in problem 66, it's asking a bunch of questions. And guys, this is very much like your test is worded too. There's a hypothesis test, and it gives you the null and the alternative hypotheses. And it says there was a random sample of 67 elements selected from the population, and they gave a mean of 46. That's going to be my sample mean, isn't it? And then they said, assume that the standard deviation of the population is 6.9, and that we want a 2.5% significance on this test. Now, for every hypothesis test, you're going to have a critical value, which is the cutoff, and which is, if it's z, it's going to be a critical z or a critical t, if it's t. And you're also going to have a test statistic, which is the observed value of z or the observed value of t. The test statistic, so you're going to have two z's and two t's, right? Every problem's going to have multiples. The test statistic comes from the sample data. The sample was taken, and this is my observation. This is what my sample test told me. Does that make sense? So there's where hypothesis testing can get a little confusing for students. All right, let's look and see what this one, I wrote down what it gave me. Basically, it told me all of this stuff. It told me the null hypothesis was that the mean would be less than or equal to 45. And it told me that the alternative hypothesis was that the mean was greater than 45. Now, if you're developing your hypothesis statements yourself from the word problems, you always set up the alternative first. This is the hypothesis statement that the researcher is interested in. This is the question that is being asked in the research, He wants to know if the mean is greater than a certain number. So he asks that. And then he says, what's the alternative? Everything else. If it's not greater than, it has to be either less than or equal. Another thing that will help you setting up your hypothesis statements is this. Equal only exists in the null hypothesis. You never find equal in your alternative. Equal only exists in the null, and it should always exist in the null. In other words, it's either going to say equal over here, less than, or equal, greater than, or equal. Equal will always be a part of it. Whereas the alternative hypothesis is either going to be not equal to, less than, or greater than. Those are just firm facts that you should memorize, okay? They gave us a sample size of 67, a sample mean of 46, a population standard deviation, which means we can use the z-table, of 6.9, and told us they wanted a 2.5% significance level. Now, before we've been saying, I want a confidence level of this, and it's been kind of different. But when they give you this significance level in hypothesis testing, they're really giving you alpha. Okay? They gave me alpha. So that's my alpha. And it's also the chance of making a type 1 error. Alpha is the chance of making a type 1 error. All right? Just saying. So I've got a 2.5% chance of making type 1 error. That's what I'm holding it to. So my significance level, and I say alpha is this. And I don't have to divide alpha by 2 because I have a right-tailed test, don't I? So this is a right-tailed test. What I would do with it is say, okay, there's the curve. There's the center of the curve. It's going to be a z-score. And my rejection region is going to be over here in the right tail. How big is my rejection region? All of alpha is over there, right? If you're looking this up on the z-table, which you are, you would look up the area 0.025. Now, I know it's on the right, but I told you, look up everything on the left, didn't I? So you go over here to the z-table, find it first. You go to the left side of it, because that's where the small areas are, and I go 0.0250, and it's negative 1.96, but my critical value for z is a positive 1.96, because this is a right-tailed test, right? So what is my critical z? Because that's what that is, critical z. Critical level is 1.96. That's where I'm going to say if my test statistic falls above 1.96, I'm going to reject the null hypothesis. If it doesn't, if it falls below 1.96, then I will fail to reject the null, and that means that, my idea, which was in the alternative, was probably not such a great one. Or maybe the data just didn't prove it, and I need to do some different kind of research. Okay? So how do we do this? Well, now we've got our cutoff. Now we have to come up with what is our observed value. What did our test, our sample, tell us? Well, our sample told us that we had a sample mean of 46. Well, I'm not really sure what this mean is. I only know what this z is. I'm assuming this population mean here is 45. Let's find out what our observed value of z is. Let's find out what our test statistic tells us. Now, one thing you should probably always do as soon as you get your data is go ahead and calculate the standard deviation of x bar. Make the adjustment that you know you have to make for every standard deviation, divide it by the square root of the sample size, and come up with something that goes to 4 decimal places, okay? So when I did that, I think I only went to 3 for some reason. Maybe it just went to 3. 0.843. I'm going to take that and I'm going to say, I need my sample data here first. Check your formulas if you're ever in question of this. I need my sample, which was 46, and I'm going to subtract the mean. Take the sample mean, subtract the population mean. What is the population mean? Guys, it's always in the hypothesis statement. We don't know what the population mean is. We're pretending so that we can do the comparison. Okay? So I'm going to say 46 minus 45 here. I've lost my place. Hang on just a second. And I'm going to divide this by that standard deviation. And I come up with an observed value of z of 1.186, or I would go to 2 decimal places with z. 1.19. Well, where does 1.19 fall? Not in the rejection region, right? It's right here. But what if they ask you for the, and so you say, fail to reject, right? I mean, that's the answer to that question. Do I reject or not? Fail to reject this one because my data didn't prove it. But what if they ask you for the p-value? The p-value is this. Always. The p-value is always equal to the area in the tail past the test statistic, right? This is the test statistic. This is observed value of z. I used to have all the parts that you know that might confuse you. Hang on. Well, to get that p-value, I have got to go back to the z-table. Once again, I need the area in the tail. I'm only going to use the negative side. I'm going to go 1.19, except I'm going negative 1.19. And here it is. It's 0.117, isn't it? So how big is this area? That's how big it is. Is p-value less than alpha is your question, okay? That's the test that you know, a lot, and that's the other side of this. Is p-value less than alpha? If it is, we reject. That's the other test, okay? If you're not drawing a curve and seeing if it falls into the rejection region, you're doing a p-value test. And so I said my p-value is 0.117. Alpha is 0.025. Is p-value less than alpha? And you would say, no, that's not, right? 0.117 is greater than 0.025. Fail to reject. It fails both tests, the p-value test and the other test. But when you draw the picture, it's obvious that it fails both tests. It's obvious because the observed value does not fall in the rejection region, and it's obvious because, look, this area, p-value, is definitely bigger than this area, right? P-value is not less than alpha, which it always has to be if you're going to reject the null hypothesis. The p-value test doesn't change. It's always the same. P-value less than alpha. Are you good? Is this a lot? I mean, I've been teaching this for many years, and it doesn't seem like, it seems like it's still a lot. Is it a lot to get? Okay. Okay. Over the years, I've tried to come up with the exact words that would help you to understand it. And the fact that we have a microphone going, and you have a video to rewind and watch. Happy Thanksgiving while you do that, right? So that you can practice. This is going to be important. Let's look at another one. This one I think I set up for you is going to be number 100 in the problem set, and it is sample standard deviation. You guys are awfully quiet, so hoping that you're just thinking. All right, so it says thousands of people nationwide are going to take part in a spring cleanup day along the highways in their hometowns. The goal is to have individuals collect an average of 50 pounds or more of garbage. There's a random sample of 36 people, and for that sample, an average of 46.3 pounds was collected with a standard deviation of 9.2. Significance level for this one is 2.5. So, what we've got to do is come up with the hypothesis statements. As the researcher, what do we want to know? Well, we want to know if the average collected, if we collect that average of 50 pounds or more, right? Sorry, hang on. I'm going to go set up my hypothesis statement. It said, first it says they want to know if they collect 50 pounds or more. Now, I could set the hypothesis saying I believe people collect at least 50 pounds. But I probably am going to say the opposite of that. And I did the opposite of that for this particular question. Believe me, you are not going to have that issue on your final exam of I don't know which way they want me to go. It'll be very clear, okay? So let's pretend that I just made this very clear. I said to you that I want you to test and see if they have collected, if the average is, less than the 50 pounds that we think, okay? If it's less than. That's where I come up with my hypothesis statement. The mean, the population mean, the average is actually less than the 50 pounds anticipated, okay? Now, what goes in the null hypothesis is the opposite of that. I did turn this on, right? And it's got to have the same starting and ending point. These are identical except for the operation in the middle. You understand that, right? So what's in the center? Well, greater than or equal to. Remember, it always has equal in it, right? So it's greater than or equal. I think people collect, and that's saying that, okay, I'm going to reject the fact, if I find that it's different, I'm going to reject the fact that people collect at least 50 pounds. In other words, I don't think they do. I think they collect less than 50 pounds. I'm the researcher. I get to set my hypothesis statement. Are you good on that? And it will be clear which way you're supposed to set it. Will be clearly worded in your problems, okay? So the next thing I have to say is, well, first, standard deviation. I've got a standard deviation of the sample that I took, and it came to 9.2. Let's fix this standard deviation and make it a standard deviation of x bar. Let's take the 9.2 and divide it by the square root of the sample size, which is going to be really 9.2 divided by 6, isn't it? Where am I? And I come up with a standard deviation of 1.5333 when I go to 4 decimal places with this thing, okay? Now, I need to say significance level 2.5%, which means that alpha for this is 0.025, isn't it? And I'm not going to divide it in 2 pieces because this is a left-tailed test. I'm going to draw it out here. This is my test. Center is always 0. What table do I use? Well, I'm given the standard deviation of the sample, not the standard deviation of the population. So I have to use the t-table. So I'm going to say it's going to be over here somewhere, my rejection region. Remember, your rejection region arrow matches the arrow in the alternative hypothesis, doesn't it? This is pointing toward the left. My rejection region is over here toward the left. And my rejection region is this big, 0.025. That's how big it is. Now, the other thing I have to use the t-table is degrees of freedom. So I subtract 1 from my sample size, and I say I'm going to work with degrees of freedom of 35. Now, I'm going to recalculate all this because I didn't use a 4 decimal t-table last time. Well, let's see what this comes out to be. I've got area of 0.025. It's a one-tailed test. Degrees of freedom 36. Whoops, wrong side. Degrees of freedom 36, area of 0.025, and a one-tailed test, it's this column. So I've got, I'm just going to see how different it was from what I did last time, okay? Really close. 2.0281 is what I'm going to use for T. Did I get that right? So I'm going to say this is 2.0281, and it's over here on the negative side. Yeah. Oh, was it? Thank you. 30, it was 30, okay, 2.0301, right? Thank you. 0301. Very good. All right, so I'm using that because, and now I just need to calculate where does my test statistic, I figured out this is my critical value for T, right? This is critical T. That's my cutoff. I've set my test up. Let's see where the test that I took fell. Let's calculate the observed value for T. I'll take my sample mean and subtract what I think the mean should be, and that's in the hypothesis statements. And then I'll divide it by the standard deviation that I adjusted, and I'll come up with a calculation that I'm going to do. I got this one. Hang on a second. I came up with negative 2.413, but I need 4 decimal places. Let me just try this. 0.3 minus 50, enter, divided by 1.5333, and I'm going to go to one more decimal place, actually. So I came up with negative 2.4131. Now, with the t-table, this is a little bit tricky. Where is that going to fall? Well, actually, with the rejection region drawn like this, I can see it falls right in here. I don't know where, but I know it's in here somewhere, right? Negative 2.4131 is definitely smaller than negative 2.031. But what I don't know is this. What if they ask me about this area right here? What is the p-value for this one? And that's the part that in the table, if you're trying to use it, usually comes up with a range of values. And I'll show you what I mean. For the t-table, when you're using the t-table, the only line you get to use is right here. Degrees of freedom, 35. You cannot vary off that line. I don't care how close you think another number comes to it, okay? So what am I looking for? I'm looking for that line, and I'm looking for an area that is going to be close to, I'm looking for a t-score that's going to be close to negative, or 2.4131, okay? Is that right? So I'm going to go over here and say 35, 2.4131 is between these two numbers, isn't it? I mean, that's as close as I can get. It's just between these two columns. I'll follow them all the way up to the top, and it's a one-tailed test. It's between 0.01 and 0.025. That's as close as I can get to estimating it, really. It's between those two. Yeah.
Are you always going to use the one-tailed test? Because that's what I was confused with when I was doing it online.
I'm always using this one-tailed test. Even when I take it and then I multiply the value by 2, if it was a two-tailed test, I would have already split that area in 2, so that I would be looking at the area for one-tailed. Okay, so I've got a 0.01. What's the area for p-value? Well, the smallest it could be, it has to be bigger than 0.01. It has to be smaller than 0.025, doesn't it? It has to be between those two numbers, which means that it has to be smaller than alpha. It just so happens that this time alpha is 0.025. What did we say about p-value? Well, we know it's less than 0.025. It is less than alpha. That's where it also passes the p-value test. So we reject it on either point, even though this one barely passes it, right? Questions on that? The p-value test for a t-score, usually when you find it, it's going to be between two numbers, or it's going to be greater than a number. Like if it comes out here, and my p-value came out on this side, it was way up here, I would say, well, it's going to be greater than 0.1. If it came out over here, I'd say, well, it's going to be less than 0.0005. I mean, that's the only way you can read this table. Okay? Not as exact as we would like. Are you good with that one? Sort of, kind of. I'll give you a second, and then we're going to do the last one, which is a proportion problem. Okay, I said for this one, I picked number 92. And it tells me this. It says there's a hypothesis test, and the hypothesis is that the null hypothesis is the population proportion is equal to 0.26. Yeah. Did I say? I'm sorry? I did that before? Great, thank you. Let's do, which one do we want to do then? Let me find another one. Anybody want to pick another one? It has to be a proportion problem. Go back to our little list here. Problem is 85. What about that one? Doesn't help us. I want to do a two-tailed test, okay? So look for a proportion problem that has a two-tailed test. All right, I've already worked a proportion problem with a two-tailed test for you, and that was the only one that was there. So we're going to have to just do one of the one-tailed tests. All right, we'll do number 85. How's that? I mean, it's just going to be a one-tailed test, sorry. But you've already had an example of a two-tailed. So let's change this one to 85. And what does it tell us in 85? I'm going to have to write it down. It tells you that you have a null hypothesis that the population proportion is less than or equal to 0.39. And your alternative hypothesis is that the population proportion, can't seem to write today, is greater than 0.39. And then it told us we had a sample size of 481, and there was a sample proportion given to us of 0.4350, and we want a 5% significance level again. I really can't write anything right today, sorry. Okay, and that's the question, right? Get it right? Okay, so for this particular one, what the first thing I'm going to have to do with it is say, well, they already gave me my hypothesis on it, so I'm going to go ahead and say this is my test. I know it's a z-test because it's a proportion problem, and proportion problems are all z-test. So, and I know my rejection region is over here in the right tail. That's the rejection side, okay? All right, so now what do I need to do? I need to find what this critical value of z is. And for that critical value of z, I go to the significance level. It says that alpha is 0.05, and that's how big an area I'm going to put over there is 0.05, because I don't split it in two. And that's the only thing I'm not giving you a good example of, guys, sorry, is splitting alpha in two. So I go to the z table, if I can find it. And I go over here to 0.05, and I say, well, it's between these two numbers, 1.64 and 1.65, and I think we did this once before. We'll just use 1.65, and once again, that is my critical z. Critical z, or critical value for z, or the cutoff value, or whatever you want to think of it as. Next, I need to come up with a standard deviation that I can live with, don't I? I can't remember what they call it in your formula sheet. Give me a second so I make sure I give that to you right. Standard deviation of p hat. Now here's my formula for it. It's p times q divided by n. And this one, it's really kind of important to me that I get this right because it requires me to use p times q, not p hat times q hat. And in proportion problems, you always have both of them given to you. You have p and you have p hat, right? So you got to use the right one to calculate the standard deviation or you'll miss it. So if you question which one to use, go to your formula sheet, see it down here, and see which one you're going to use. Underneath it says p times q, not p hat times q hat. There are other places where you use p hat times q hat. I'm just telling you, that's where you be careful. I know you have a multiple choice test, and a lot of you think, well, if I found the answer, you know, it must be right. The obvious mistakes will be on the test. It will be one of your answers. So that answer that I just told you to watch out for, where the standard deviation of p hat times q hat is used instead of p times q, it'll be one of the choices, right? So you got to know what you're doing here. So anyway, I'm going to say standard deviation of p hat is equal to, well, I know what p is. I'm going to say p is what they're thinking it is in the hypothesis statement, and q is going to be 1 minus p, right? Wow, I can't even subtract today. It's 60.61, right? Still have a cold. All right, so now we go. Square root of 0.39 times 0.61 divided by, well, how big was the sample size? 481, and I think I already did this one. It came out to be 0.0222. Okay, I'm ready for where does my test statistic fall? That observed value for z, the test statistic, is going to become whatever I think or whatever I came up with in my sample minus whatever the hypothesis statement says, and I'll divide by that adjusted standard deviation. And this time I come up with 2.027, which I would go 2.03 for that one. Okay. And I'm going to say, where does it go? Well, it's way over here, isn't it? So this is going to be reject the null hypothesis. Is going to be my solution, reject the null hypothesis. What's the p-value for this thing? Well, all I have to do is go to 2.03. Once again, just use the negative side of the z-table, okay? 2.03 over here would be a negative 2.03, and I'm going to get 0.0212. Okay? Is p-value less than alpha? Look at it. Is this decimal less than alpha, 0.05? And you can see, yeah, it is, right? The only thing that dividing, and we did this last time, so I guess I don't have to go through it again. The only thing that the two-tailed test does for you is it splits it. You have alpha on both sides, alpha divided by 2 on both sides. So when you do that p-value comparison, you're not comparing is p-value less than alpha divided by 2. You're saying is p-value less than all of alpha. So it's all of alpha put back together. So when you find the p-value, you're going to find, what is it on one side of my test and multiply it by 2, and that's the reason for it. You're comparing it to all of alpha, but you're only going to find the value for one side because your test is only going to fall on either the left or the right side. When you take a sample, it's either going to be, I came up with a sample that was either high or low. It can't be both, right? And that may explain it a little better. Okay. Give me a second. I want to look at and I haven't looked at it yet, so I want to look at your schedule real quick because this is the last time I see you guys before we come back from Thanksgiving. Yeah, that's what I was afraid happened to us. Really don't like your schedule very much because when we come back from Thanksgiving, we come right straight into your final exam. So this is what I'm going to do. I have office hours usually on Sunday nights from 5:30 to 8, and I have really kind of have a choice. I mean, I'm going to choose not to do those 5:30 to 8 office hours this week, this Sunday night. I'm going to put them right after Thanksgiving. My family's going to really hate this, but that's where I'm going to put them, okay? So before you have the test, I will have office hours on Sunday night, just before you come back, and I will also have them on Tuesday night, 5:30 to 8. They're virtual. You can find me in virtual office hours in Blackboard. Any of you need help doing that? Do you know where I'm talking about? Virtual office hours Blackboard, and I'll be there on Tuesday night before your final. The next time I see you, you need a Scantron, you need a calculator for your test. Everything else I will have, it will be on the test for you. The T-table, the Z-table, the formula sheet will be there. It is all multiple choice. You're used to that by now, okay?
How many questions is it?
Has 25. And don't forget, I mean, I know these problems are running through your head. I got to learn how to work these problems. Do not neglect the concepts that we talked about last week in here. Please go back through what I told you was important, because I did a really good job of telling you what was important last week, all right? You might want to replay that tape before after Thanksgiving, when it's fresh in your mind, okay? And then it's done, guys. We're finished the semester. I mean, can't believe it, but it did happen that quickly, okay? Anything else? Any questions before I let you guys go? All right, have a wonderful Thanksgiving. I'll see you